And welcome back. So this is the 8th class in our course, and now that we know what radiation is, what the nucleus is, how come that radiations happen, why do nuclei decay, and everything like that, we know about nuclear reactions. Now maybe it's time for us to start talking about what happens when radiation faces matter. And why does that matter? Yeah, well, first of all, if radiation didn't interact with matter, we would have very little use for it. It would be like, for instance, the neutrinos I showed you before. Neutrinos, they do not interact with matter, so they have very little application. They interact very, very weakly. They have almost no application. There's almost no reason for us to do anything with neutrinos. Unless we're talking about understanding matter, then it's another beast, right? But radiation, you may know, we use them for a lot of stuff. And we use it mainly because it interacts with matter. You may also have heard that radiation is bad for your health. Yes, and that's because it interacts with matter, in this case, the matter in your body. So let's talk a bit about what is this thing? How does radiation interact with matter? Usually, let's remember that the nucleus is a very tiny thing, 100,000 times smaller than the atom itself. So I think it gets somewhat clear that radiation will interact more strongly with the atom itself, right? Radiation comes here, it's much more likely that it will interact with these electrons here that spread all over than to find a nucleus to interact with. So essentially what we have is atomic or molecular interaction. Electrons interact with radiation. And they can interact in two ways. You either ionize the atom, meaning radiation takes away electrons from the atom and the atom gets ionized, and that's why we call a series of radiations, especially the ones we will study here, ionizing radiation, because they can ionize the matter, right, producing ions. Or excitation. In excitation, the electrons are only promoted to higher energy levels, and then they will come back emitting X-rays. Okay, there's also the possibility of nuclear interaction, but it's much less likely, and it's usually due to nuclear reactions, which we studied last class, right? So there's some additional references for interaction of radiation with matter. Let's just put one thing clear. It's a very, very wide area. So I'll just give you a brief introduction to what it is and some general knowledge that can help you understand roughly what happens, what doesn't, how can I avoid getting hit by radiation from something, and this kind of stuff, right? So for this purpose, we have two very good books, which are W.R. Leo, Techniques for Nuclear and Particle Physics Experiments, and Glenn F. Knoll, Radiation Detection and Measurement. Both are easy to find, especially the Knoll one. They are essentially aimed towards detection of radiation, but if you want to detect radiation, you have to interact with it. So they end up being very complete and thorough in the part of interaction of radiation with matter. You don't need these books to understand my class. Those ones in the bibliography are okay, but if you want to go any further in this subject, these are very good books to see. Okay, so two things radiation can do. First, it can, with electrons, the particles, whatever they are, they can interact with an electron and eject an electron, leaving a positively charged atom and a rogue electron here. This is ionization. It can also do excitation, where it gets an inner electron, promotes it to an outer shell, where there's a vacancy, it can fit, right? The incident particle goes away, and then the excited atom ends up decaying to its fundamental state and emitting X-rays. Okay, we have to separate the processes in which different types of radiation interact with matter are very, very different, fundamentally different, and I can somewhat show you why. First of all, we have charged particles that those particles have charge, and if they have charge, they can interact directly with the charge in the electrons, and that's one thing. And then we have neutron particles, where interaction is a bit more indirect or tricky. And even inside the charged particles, we are talking about interacting with electrons, right? So when one electron interacts with an electron in an atom, there are particles of the same weight and everything. That's one thing. When a heavy ion, meaning even the lighter one of these ones, which is a single proton, interacts with an electron, we're talking about something that is 2,000 times heavier than the electron. So it's a completely different interaction, right? So we have to separate this interaction of charged particles in heavy and light ones. These are the ones we will talk today, these two. Next classes we will discuss how photons and then neutrons interact with matter, because as they don't have charge, they don't interact straight away with the electrons. So, charged particles. Essentially what you have is charge and charge. Charge of the particle that's entering the system, and the charge of the electrons in the system. They happen with individual electrons in the atoms, meaning the particle, whatever it is, interacts with one electron and either ejects that electron or promotes that electron, and then you have excitation, right? But then there's the chance that the particle that's entering will interact with the nucleus as a whole, right? I'll talk about it a bit later. And then there's a chance, if the incident particle has very, very little energy, it can interact with the atom as a whole, not with the nucleus, not with the electrons individually, but with the atom as a whole, right? This is called coherent scattering. We talk very little of it here because in this case you don't have residual radiation, and the incident radiation loses very, very little of its energy. So there's very little use for that the way we study it, okay? There's people who use that for other things. It's called Rayleigh scattering, and that's another beast, okay? So now let's go to more specifically, not only charged but heavy charged particles. What I mean by heavy is at least a proton. And then we're talking about something that is 2,000 times heavier than the electron, right? And anything else that we have, either it's an alpha particle, it's a carbon beam, or something, is heavier than this, so the difference is even larger. So okay, we talk about a very, very heavy particle inciding on a light one. It's 2,000 times difference in weight. So first thing, it loses energy mainly by collisions with electrons. And now try to picture you have a bowling ball and you throw it, and you have all those very, very little plastic balls, light ones. The bowling ball will just go on scattering those little plastic balls everywhere and lose very little energy in each contact, but will stop rather quickly because there's just so many of those small bowling ball plastic balls, and it stops quickly, right? That's essentially what happens. So these heavy charged particles, they lose very small amount of energy in each collision. think bowling ball against plastic ball. But given the mass difference, you can understand that the bowling ball will not change its trajectory. It just goes straight and the other particles go away. That happens with the nucleus also. So even a proton, the lightest of the ones, when it enters matter, it just goes on splitting, just throwing electrons all the way out. But as it is large, it will interact with too many electrons at all times. So it means that the trajectory will be linear, because it won't change direction because of these small things, but it's essentially very short because it interacts with everybody, right? So it loses a very little amount of energy in each collision, but it will collide with quite a lot of things. It will stop at anything, and by stop I mean it will collide with anything. So very shortly it will stop, but it will do quite a lot of damage in this path, right? So here we have, for instance, ionization traces produced by heavy charged particles. All of them had 10 MeV per nucleon, and they are entering a photographic plate, right? So you see that the trajectory is indeed very, very linear, as I told you, right? And you see that the heavier they are, and remember, it's 10 MeV per nucleon, so 120 MeV and 140, 160, so you see that even increasing the energy, the path is shorter for the heavier ones, right? Just once again, remembering you, mass number should not be on the top right, but this is a notebook I took it from, so it happens. You shouldn't do it, okay? You should always put it on the left top side. Okay, so this is what happens. You see, very straight trajectory, and if you take a closer look, you'll see that the damage in the start is not that big, and it starts to increase more towards the end, right? The heavier they are, the more pronounced the damage in the end is, right? Well, that has to do with the way the particles interact with matter. We define this interaction by its linear stopping power. And no, I don't expect you to have this in mind, to have it decorated or something. It's just for you to understand, essentially, right? This is not something I would collect in a text. Not these equations. So, linear stopping power essentially is how much energy the particle loses per unit depth. And the fact is that this depends on the energy, and it decreases with the speed, or linearly decreases with energy, meaning that the more energy the particle has, the less likely it is to stop, right? So the part, as I showed you here, particle, when it's with all its energy, it interacts very weakly, so very little damage here, just essentially was straight in front. And as energy decreases, you see that because it's entering, it's interacting, and it's losing energy. And as it loses energy, the interaction becomes more strong. And you see this very clearly here, right? Start of the line is very thin, and it starts to get thick with lots of damage towards the end, which is where the particle has less energy until it stops. And one other thing that you should notice here is that the stop is very precise, right? You don't see the light becoming thinner and thinner and thinner and vanishing. No, it goes up here and then disappears, right? This is a characteristic of the heavy ion interaction with matter, right? So the stopping power depends on the energy. The higher the energy, the lower the stopping power, meaning it loses less energy per depth. It depends on the charge of the particle, right? Because as we're talking about electromagnetical interaction, the more charge the particle has, the more the stronger is the interaction of it with the electrons. So it goes with the chair Z squared. And also it changes with the density of the medium, which is quite natural because the more atoms you have on the medium, the more electrons you have on the medium, and so the more the faster, stronger will be the interaction, shorter will be the path, right? You have too many collisions until stopping, but it collides with everything. So in this case, the range is short, but is really well defined, as we saw here, right? They stop here. There's not a trace of anything going further than this. And you don't have any hint that something started to stop before this, right? The lines, they finish very abruptly on the end of the path. Well, these are the heavy ionizing particles. And if you look here at the specific ionization of an alpha particle in air, meaning the number of ion pairs it produces per millimeter of path. And this is true for air, and this is true for every single medium. And this is true for alpha particles or for other charged particles too. If we take a look, so it produces a reasonable amount of ion pairs, but not that much. And as it enters matter, because here is the final range. So here the particle is entering from here. They have high energy, so interact little. And then they start to lose energy, and they start to interact a bit more. And as they interact more, they lose more energy and start to interact even more, and lose more energy and interact even more, until it reaches a place where it interacts so strongly that it leaves all its energy right there. And if you see, this means that the particle will deposit all its energy, or more than half of its energy, on the final part of the trajectory, right? As we can assume here, right? There's a little energy deposited here, and you can see a lot of energy deposited here, right? So this is a very important thing, and we have a very important use for that in medicine or in industry. So this is a very important thing about heavy ionizing particles, heavy charged particles. They deposit most of its energy at the end of the trajectory, and they have a very well defined range. This means what? That it does a little damage on the entrance, a little more damage through the middle of the path, and a lot of damage in the end. And they will all stop, because what happens when an ionizing particle reaches the end of its path? It stops, and now it's just an atom that is deposited inside your target, right? Now just giving you a glimpse of, because I'm saying here that all particles will stop essentially at the same place. So if I want to, I have a crystal, and I want to just deposit ions here, right? I want to make an electrode here, so I want to deposit ions at a very precise depth inside this crystal. You see that if I use charged particles, accelerated charged particles, heavy charged particles, I will deposit them at the thickness I want, because I increase a bit the energy, I increase a bit the depth, so I can deposit these particles really where I want. This is called ion implantation, very used in semiconductor industry. And yes, they use accelerators of heavy charged particles for that. And it's very, very precise to less than 1 millimeter. Then there's another thing we can think here, because I said, okay, there's a bit of damage here, a bit more of damage here, but the most damage is done in this last part here, right? So imagine if I could point this thing to a tumor and just tune the energy so that the worst part of the damage would happen inside the tumor and not in healthy tissue. More than that, I can assure you that after the tumor, there's absolutely no dose. This could be something, right? Yes, there is. This is used. This is called hadron therapy, proton therapy, or something. We'll talk about this when we talk about medical applications, right? So this is a characteristics of interaction of heavy charged particles with matter. Just once again, remembering, heavy charged particles are anything heavier from a proton up. So can be a proton, can be an alpha particle, can be carbon atom, whatever. Just something heavier than a proton, from a proton up, okay? So this is what happens with heavy charged particles. We'll come back in a minute. Just let's go one step back now and say, okay, now what happens with a light charged particle? Light charged particle is essentially an electron or a positron, right? So now we're not talking of a bowling ball hitting some little plastic balls, right? Now we're talking like snooker, right? We have two balls of the same size, same weight, both are electrons, or one is an electron, one is a positron, and they will hit. So what happens when you're playing pool? You're there playing pool, or depending on the place, it's pool, snooker, right? You have the balls, you have the stick, and okay, you just hit, and balls hit each other, and then you know one thing, right? There's times when you hit the ball and it will stop at the first ball it collides and transmits all its energy to the other ball. Most times, though, it will transfer part of its energy and the other one will have significant part of the energy. So, in average, in each collision, if the two balls are exactly the same size and weight, which is the case, you will lose, in average, half of your energy in each collision, right? And this means that every collision you lose half of your energy, but now you have a second particle with a part of your energy which is also an ionizing particle now, right? So you see that we start to have less interactions until it stops, but you can produce more disperse damage, right? And there's another thing too. Think snooker pool or pool table. There is the chance that the ball is not, it's not sure that it will hit the first ball it passes through. It may pass straight away from the first one, from the second one, from the third one. Imagine you're playing in a pool table, you have some balls there, and you're blindfolded. When you do that, you may collide your ball with the first one, just straight ahead. But it may also go all the way until the end of the table without hitting anything, right? So now it's not like the heavy charged particles that would interact with everyone in front. No, this is a more sophisticated thing. It goes and sometimes it will hit something and then lose a significant amount of energy and change direction significantly. But it may also just go on and take a while until it finds something, right? So now you see why these collisions, we have to study light charged particles separately from heavy charged particles, right? They are completely separated things. Well, for light charged particles, there's two processes that can take place. Collision, which is the same that happens with heavy charged particles, but there's also radiation, which has this very nice German name here. In German, you should say Bremsstrahlung, which is Bremsch is break, Strahlung is radiation. So it's breaking radiation, right? Name says it all. It's when the particle reaches, you have a nucleus here, the particle goes very close to this nucleus and then it fills the electric field of the nucleus, and it's scattered or either inwards or outwards, and then just for conservation of momentum, if it does this, it has to lose a part of the energy because the nucleus has to have a little bit of recoil energy too, right? And the total loss is the sum of both losses, right? For low energies, collisions are much more likely, right? For higher energy, radiation starts to dominate. Most of the work we do here, for instance, we're talking about lower energy, and then collision is more dominant, but radiation is always present. Well, what is this radiation energy loss? If you have an electron here, and first of all, let's talk something. Okay, this happens to an electron. Let's talk about it, then I go there. Okay, the electron comes here and it reaches very close to the nucleus, right? And then it will be oh shit, forgot. The electron is close to the nucleus, then it is the electrical charge in the electron is brought towards the nucleus because of the electric field, right? You have an electric field, the electron will deflect towards the positive particles, and then it will do something like this, and you have a gamma ray here. It's not a gamma ray, we call it an X-ray because it's made by electrons, and it's a Bremsstrahlung photon. And this, in fact, can reach several kilo electron volts, up to 200, 300 kilo electron volts. So it's a very energetic X-ray, right? When that happens, the electron loses part of its energy, right? Because if we emitted this energy, it was lost by the electron, right? And that's what happens. And then, of course, an electron will be deflected towards the nucleus because it's attracted to the positive charge, and the positron, on the other hand, it will be deflected away from the nucleus because it is repelled by the positive charge, right? So that's breaking radiation, which is dominant at higher energies. Now, when we talk about collisions, there's another thing, because as I said, the mass of the incident electron it is equal to the mass of the atomic electrons it is colliding with. So, as we all know, the electron will lose approximately half of its energy on average in each collision, right? So it's a large energy loss in each collision, not like the heavy charged particles that lose a very infinitesimal part of its energy in each collision, right? This means strong decelerations, this means large direction changes. Once again, think of a pool table or snooker table, whatever you may call it, right? And the trajectory is not linear at all, unlike the heavy particles, right? So in a heavy particle, the path is equal to the range, meaning it will stop at the end of the path. And the path, if you take the length of the path, it's equal to the depth it entered. Here it's not, because the path is much larger than the depth it entered, right? Now it's a good time to define what range is. Range is the depth to which the particle penetrates matter. It's not the length of the path inside matter, but the depth you need to stop that radiation, right? And looking here, you see that heavy charged particles, they have a very well defined path, right? Range, because it's equal to the path, and they lose very little energy in a very lot of collisions. So it's a statistical process and on average you will stop at the same point always, as we saw on the pictures. Now for an electron that's different, because if this band had been towards this size and not here, the range would be much larger. If this one happened to be backwards, the range would be much shorter. So the range of electrons and light ionizing radiation in matter is much smaller than its path, and not so well defined either. Right? So, some ideas that are important to put: the greater the energy of the particle, the larger will be the range for the same kind of particle, right? Because if I have more energy, it will take more collisions until it stops. And of course it's clear that different particles with equal energies will have different ranges. In fact, very different, right? So just getting now a glimpse on what happens in our world. So we talked today about heavy ionizing radiation and light ionizing radiation. But the heavy charged particles, heavy ionizing radiation, they have masses thousands of times larger than the electrons they collide with. The light ones, they are exactly the same as the electrons they collide with. Taking an example, because we know that nuclei tend to decay via alpha or beta decay, right? So an alpha particle, it interacts it is clearly a heavy ionizing particle. It interacts very strongly with matter. It has very high ionization power, meaning what? Meaning it will deposit a lot of energy in a very short path, right? And on the other side, if we think that the damage something does to a medium has to do with the amount of energy it has deposited in that medium. So if we think an alpha particle, it has a range in air of a few centimeters, and in solids it can be down to micrometers. Thinking now, it has, I don't know, let's say it has 4 mega electron volts. It will deposit all this energy in a micrometer or 10 micrometers of medium. You see, it does a whole lot of damage in that small place, right? Now, if we think beta rays, the interaction is much less intense, meaning it will have a tortuous trajectory. That's another thing, and these two things together also mean it will take much longer. So they interact less intensely, their path is longer, so what happens? The range in the air is meters. Oh, I forgot to translate here, sorry. The range in the air is meters instead of centimeters. It's several meters in this case. And the range in solids go from micrometers to several millimeters. Even more than that, maybe 1 centimeter. Usually let's say 1 centimeter, half centimeter is good. So you see, they take a lot longer to stop, meaning that they will deposit, supposing they have the same energy as the alpha rays, I suppose it's thought of 4 MeV, they will deposit all this energy in a much larger place. So the damage will be not as intense as it was with the alpha rays, right? So think, alpha rays, they do a whole lot of damage in a very short range. Beta rays they do the same damage, but distributed towards almost 10 times more space, right? So, let's go here. This is essentially, we're talking about an experiment. You have a source, you have an absorber, and a detector. And then, if we go on increasing this absorber, we will get, right? And in this case, forget about the scale here. shouldn't be millimeters, should be something else, but forget it. Should be micrometers here. But you see, it goes on, and I go on increasing the absorber, and the same amount of radiation is reaching. Just remember, it's the same amount of radiation, but it's a bit less energetic. It has a bit less energy until it has very little energy, and then it starts to stop. So you see, as we saw before, a heavy ionizing particle will go all this way, only losing energy, but will not stop. And they will all stop at the end of the trajectory, thus we start to lose luminosity in our detector. Right? When we talk light charged particles, you see the thing is different. Right? We take a look, and it starts to lose intensity right away, because in just one collision here, it may deflect from the path and not reach the detector anymore. So there's not this plateau you see with heavy charged particles. You see this plateau, just to make sure you understood. You have this plateau because they are losing energy, but they are not changing their trajectory or stopping. So they are all going just with less energy, but they're still counted, and they go further, they lose a bit more energy, but they're still counted until the point where they just start stopping. And that's only on the very end of the trajectory. With electrons, it's different. You do not have a plateau, because in one collision you can take the electron away from the beam, and then the electron won't find the detector on the other side, right? It will be deflected to another place. And it goes, and you don't have that abrupt end either. You have a smoother end, because there's always a little chance that one electron could go a bit further than the others, because it just had grazing collisions with other electrons, and so it didn't deflect really that much, and it will go further, right? So this is important. Electrons with the same energy will not have the same range, so they will not stop all at the same place. And one thing that's important to say, I told you that heavy charged particles, meaning ions, they will enter matter, lose their energy and stop, and then they are just ions that are deposited inside your sample. Electrons, it happens essentially the same. They go on and they start to lose energy and start to lose more energy, and they reach a point where they are simply, they have almost no kinetic energy, and they are essentially just another electron in the medium, just like every other electron that was there. Okay? And for positrons, I think it's important to say now, positron, when it has high energy, because we always think positron, antimatter, it will collide with an electron, which is matter, and then they will disappear. This essentially happens when the positron has almost no kinetic energy. We call it the annihilate at rest. When it's still traveling, it still has considerable amount of kinetic energy. We call this in-flight annihilation. And in-flight annihilation is very unlikely. So what happens? The positron, it will interact with matter just as if it was an electron. It will scatter with other electrons. It will take other electrons from it, their atoms, and it's only at that point there only one small charged particle going. And then as they do that, they start to lose energy, and when they are in a very low energy state, they have very little kinetic energy, then they will find an electron and annihilate, producing two opposite 511 kiloelectron volt gamma rays. Okay, we'll talk about that later, but I think it's important to just put this now. So This is how a light ionizing particle interacts with matter. And now the scale is correct. Right? It goes on and start to lose energy, and they start to lose energy, and they lose intensity too, not just energy but also intensity, right? Because every scattering it does, it may be removed from the beam and go away. And the end, if you take a look here, there was although the curve is doing this, you can notice that it would be really a curve like this, right, with the tail here, because there's always the chance that one electron will go deeper than the others. So one image is worth 1,000 words. So we'll give you 2 images. Yeah, alpha rays. And for alpha rays, the same thing goes for every heavy charged particle. It will be true for protons, it will be true for carbon ions, or whatever you have. Right? They will interact really strongly, and as they are very much heavier, their trajectory is essentially linear, and they will stop very quickly. On the other hand, a smaller particle, the electron, which is 2,000 times lighter, it will scatter with those pairs. The electrons it scatters into are just as it is. Same weight, same charge, same everything. So they just go on scattering, and the path is much larger than the range. And even so, even with that, this range is much longer than this range. Right? So, once again, when an image is worth 1,000 words, let's just sink in, take a deep breath, right? Once again, remember that this one should be micrometers, not millimeters. You have, if you see, it goes, and every single particle is counted. I go on increasing the absorber, and every single particle is still counting, because they are losing energy, but they are not losing all their energy, so they're not stopping, and they are not deflecting from the beam, so they're still going towards the detector. And then in the end of the trajectory, they stop really abruptly. While if you look at electrons at a very small depth, you start to lose electrons from your beam, and that's because you can't, in a single scattering, the electron is scattering something just his size. They can go one way, the other one goes the other way, and you lost. There's nothing reaching the detector anymore, right? And the range of heavy particles is of centimeters in the air, which means that if I have a source here in my camera, here, I will not be, it's an alpha source, I'm not having any I'm here, I think, 70 centimeters away from the camera. There's no chance any radiation from that will reach me, because it's an alpha particle, right? If I put a small amount of plastic, I just decide to wrap it in paper, right? Paper is a lot more, is thicker than a few micrometers, so the alpha particles will not escape. So alpha particles, if you want to have an alpha particle source, it cannot have anything above the source itself, because everything you put there will start to take energy away from your alphas, and a few micrometers of anything will just stop them. If you want to have an idea, if you have aluminum paper, right? If you wrap an alpha source in aluminum paper, you essentially make sure that alphas do not escape anymore, right? This is not true for electrons. Electrons will have a range of meters in air, meaning that if there's a beta source in my camera, I'm 70 centimeters away, it's reaching me fine. I'm taking electron from the electrons emitted by my camera. If I was, I don't know, where that other chair is there, down there, still wouldn't be feeling beta particles getting to me. I would have to be a few meters away to be safe from this, right? And in solids, they can penetrate centimeters, or in lower energies, millimeters, meaning that I usually need some kind of solid that is half a centimeter thick or something to stop. And now there's a trick here. It's not an important trick, but it's important for you to have that in mind. Remember, I told you that light particles, they can interact also via Bremsstrahlung, via radiation, right? And radiation is more likely for heavier media. If your scattering media is hydrogen, there's very little radiation happening. If it's, don't know, lead, there's a lot of radiation happening. And radiation causes the emission of X-rays, which are bad for your health. So you find out that most beta sources, if the strongest radiation they have is beta particles, they will be encapsulated. You have, if you take a look at labs here, you will sure find an old wooden box with sources inside. It's because wood has low atomic number, meaning low radiation, and at the same time it can stop because it's more than half a centimeter thick. So it stops the beta rays without producing too much Bremsstrahlung radiation. Right? If we got the or you had the source and you encapsulate it in a polyethylene, for instance, or nylon or something, some plastic, because once again we have low Z material, you will have loss of beta rays without losing that, creating that much Bremsstrahlung. If I had a source and I just wrapped it into a metallic strip or something, we would have a lot of Bremsstrahlung going on there. Okay? And that's all we had to say about the interaction of charged particles with matter. Remembering, I know I have already said that on this slide really, but heavy charged particles, meaning protons, alphas, and everything heavier than that, they will interact one way. They will interact very strongly, very short range, a lot of damage in a very short space, right? So for instance, if you have an alpha source here over my arm, it will damage my skin but will not touch the inner flesh. If I have a beta ray, it's different. It takes longer to stop, so it will dilute its damage throughout this larger trajectory. Meaning that if I have a beta, if I have just put a beta source over my arm, it will deposit part of its energy in my skin, but part of the energy will go to muscle and some, maybe even a bit on the bones. But it's less concentrated, meaning that if I have an alpha decaying material in my skin, I will have a lot of damage in my skin. If I have a beta emitting, it's less damage in more space, right? And this is probably the most important thing here. Heavy ions, you can shield them with air, a few centimeters of air, and you're good. Or you wrap it into aluminum paper, you put them, whatever, you don't need to overthink it, just wrap it somewhere. On the other hand, if you want to measure them, you must have nothing there. And that's why if you take a look at alpha detectors, they are usually, alpha detection happens in vacuum because of that. For light particles it's different. Their range is of meters in the air, so you have to go far. Air is not that good of shielding. You would have to use solids, and then you would rather use a few millimeters or even a centimeter of something of low atomic number to avoid problems with Bremsstrahlung, because Bremsstrahlung is stronger for higher Z materials. Okay, so that's it. That's all I had to say about these for now. Okay, see you later, alligator.